esteemed viewers, this is Medical Science Lecture Room. I am delighted to have you back. In this channel, we run lectures or classes on physics, chemistry, and mathematics. We also teach our viewers at the comfort of their living room on medical conditions. That is to say, we give medical tips or medical education to our esteemed viewers to enable them stay healthy. But for today, our discussion is on chemistry and the topic is hydrogen bonding. Once again, my name is Dr. Godwin Obono. In case you're new to this channel, please do not fail to hit the subscription button. Also, turn on your notification bell so that once new videos are made, you'll be first to be notified. Again, like the video and share. Let's begin. Welcome back. Like I told you, today the discussion is on hydrogen bonding. I have done videos on ionic bonding or electrovalent bonding, covalent bonding, and we said covalent bonding can be divided into ordinary covalent bonding and coordinate covalent bonding. Please, I will drop the link for these videos. I want you to access those videos so that you have adequate understanding. When you read when you watch those videos, then you combine it with today's lecture. Today's class is on hydrogen bonding, and so when you put all of that together, you have a proper understanding of what chemical combination. So hydrogen bonding, I will begin by telling you what hydrogen bonding is. Hydrogen bonding is defined as a dipole-dipole interaction between hydrogen and an electronegative element. I take it again. This is a dipole-dipole interaction between hydrogen and an electronegative element. Now, I have mentioned the word dipole-dipole. Now, let me explain what I mean by dipole-dipole interaction. But before that, I need you to know that hydrogen bonding is an intermolecular bonding. It's an intermolecular. The word inter, it means that it is a bonding between one molecule and another. Unlike when we look at a covalent bonding, we were not dealing with molecule. Rather, what we were having is one atom will share electrons with another atom. For ionic bonding, one atom will transfer electron to another. But in this case, it is not atom, it's a molecule. One molecule will interact with another molecule. And so when one molecule interacts with another molecule, you will have an intermolecular bonding or intermolecular interaction. An example of such intermolecular interaction is hydrogen bonding. So one common example is the molecule hydrogen fluoride. Remember, I just took hydrogen fluoride. Hydrogen fluoride is written this way. This is hydrogen fluoride. Remember, I told you it is the dipole-dipole interaction between hydrogen and an electronegative element. Now, this is a molecule. This hydrogen fluoride is a molecule. If hydrogen fluoride is to interact, if it interacts with another molecule, then that may likely be an intermolecular bonding or a hydrogen bonding. Now, take it again. What is this bond? This is a bond. This bond is formed by covalent bonding. Which is why I said go and read and watch that video on covalent bonding. You will see we even describe it using this example. Now, this is a bond formed by covalent bonding, and now this bond has two electrons. One of those electrons came from this hydrogen, the other from fluorine, and so they both share this electron equally, leading to this bond, and this bond is called covalent bond. Now at this point, because hydrogen fluoride want to interact with another molecule, what happens to it? What will happen is this fluorine, because fluorine is more electronegative than hydrogen. Again, look for my videos on electronegativity. It's very important for you to understand all this concept. Now, fluorine is more electronegative because electronegativity decreases down the group and increases across the period of a periodic table, which is why the group 7 element are the most electronegative element. So if you see fluorine here, it means that fluorine is more electronegative than what hydrogen. And if fluorine is more electronegative than hydrogen, it therefore means that this bond that you see, fluorine will be attracting more of the bonded electrons to itself. Remember that the bonded electrons are 2. Now fluorine will be attracting more of the bonded electrons to itself. But it's not as if the bond will be broken. No, it's not as if the two will separate. No, but because this fluorine wants to change its appearance, and because it has to change its appearance so that it can interact with another molecule, so this fluorine tend to attract more of this bonded electron to itself, because it's more electronegative than this hydrogen. Being electronegative means it has the potential, it has the ability to attract electrons. So what that happens, the moment that happens, this fluorine becomes partially negative, because it tends to have more of the electrons to itself, while the hydrogen becomes partially positive. Why is it partially positive? Remember that if I have told you that fluorine attracts more of the bonded electrons, initially it was 2 electrons. Supposing fluorine attracts 1.5, it means that the hydrogen will have less of the electrons. Remember that electrons are negatively charged, and because they are negatively charged, the fluorine that comes to have excess of it will now show that by having a partially negative end, and that's why we have it written like that. Now this molecule at this point is called a dipole. It's called a dipole because it has 2 poles. This is a pole, this is a pole. It's like having north and south magnets, or a positive charge and a negative charge. These are also polar. Now at this point, this is hydrogen fluoride. It's now a dipole. Now if hydrogen fluoride now interacts with another hydrogen fluoride, you may see another hydrogen fluoride here. Let's say this is another one. Of course, what happens to this will happen to this other one. This will be partially negative, this will be partially positive. Now you can now see this is a molecule, this is a molecule. By the time you see, the 2 molecules will now attract themselves, and so throw positive to negative, throw positive to negative, or negative to positive. And so this interaction, because here is positive center and here is negative center, so the attraction can occur like this way. And so once that happens, you say this is hydrogen bond. Why is it hydrogen? Because it involves hydrogen. Look at hydrogen is here. In every situation, every time you see hydrogen bond, there must be involvement of hydrogen. So because there is hydrogen here, so it is called hydrogen bonding. So again, this is a molecule, this is a molecule. Because it involves 2 molecules, it becomes intermolecular. So intermolecular bonding. So you see that in hydrogen bonding, you see that in hydrogen chloride, you see that in hydrogen iodide. It's usually hydrogen with loose non-metals, group 7 elements. So when you have this, that is simply hydrogen bonding. And that's why I say it is a dipole, because this is a dipole and this is a dipole. That's why I say it's a dipole interaction between hydrogen and an electronegative atom. Okay, now let's quickly look at the importance of hydrogen bonding. Why hydrogen bonding chemistry is very important. The reason is that it is implicated in boiling points. The reason why some molecules have high boiling point than expected is because of their ability to form hydrogen bonding. Such molecule like water, for instance, we say water has a high boiling point. You see alkanols. An example, of course, of alkanols is ethanol. Also carboxylic acid. This molecule have high boiling point. The reason is because they are able to form hydrogen bonding. What is boiling point? Boiling point is a temperature at which a liquid will vaporize. So it means that they are all liquid form. This molecule are in the liquid form. When you want to convert them to the gaseous state or vapor state, you need some level of heat or amount of energy. And that energy, that heat that you need to convert them from their liquid state to vapor state is that temperature at which that happens is what we call the boiling point. Now, quickly, I want to tell you, sometimes you will see questions like between alkanoic acid and alkanol. You see question and alkanol. They will tell you in some exams what you should account or explain why there is high boiling point in alkanoic acid than alkanol. So, or example, this we can have here ethanol, we can have here ethanoic acid. Sometimes they can give you explain why there is the boiling point in ethanoic acid is higher than the boiling point in ethanol, or why the boiling point in alkanoic acid, which is the family name, is higher than the boiling point in what alkanol, which is the family name of what the ore. Okay, now let's explain that. Let's see. For me to give you answer to that, I would like to draw the structure of this. You know that alkanoic acid, this is their general formula. This is the general formula of alkanoic acid. Now, if one alkanoic acid is to interact with another alkanoic acid, remember, in hydrogen bond, we are looking at what intermolecular interaction. So, one alkanoic acid, for example, we say ethanoic acid. You want ethanoic acid is to interact with another ethanoic acid, or ethanoic acid is to interact with propanoic acid, or propanoic acid wants to interact with butanoic acid. The most important thing is that one molecule, one alkanoic acid molecule, is interacting with another. So if of course, all of them, they have the general molecular structural formula as this. Now, in this form, in this form, this bonding cannot take place because of what the location of this double bond. The double bond here makes it not possible for that interaction to take place. So this is what happens. This double bond, one of the bond will shift to this point, and that's what we call mesomeric shift. There will be a shift of this bond, one of them. Remember that these two bonds you see, one is a sigma bond and the other is a pi bond. The pi bond is assumed to shift. You transfer it, and if that happens, this is what you see. You have this. There will now be only just a single bond there. This one that has been transferred, you see it here like this. It will be placed on top of the oxygen, and then you have this. Why this is happening, now you can now see that this end has a partially negative center. It's partially negative, while this other side is still neutral. So, but what happened? For this bond, this oxygen itself is negatively charged, is more electronegative than hydrogen. So this bond, of course, this bond is formed by covalent bonding, ordinary covalent bonding. So what you see is that this oxygen will attract more of these bonded electrons to itself. Therefore, this oxygen becomes partially negative, while the hydrogen here become partially positive. Now, this is how it will now appear. At this point, it is ready to interact with another molecule. And if it interacts with another molecule, that molecule will also appear like this. Now, if I take the other molecule, I write it here. This is the other molecule. It doesn't matter. This is another molecule. What happened to this will also happen to this. And so here will be partially negative, here will be partially positive, this is partially negative. And so this molecule is the same as this. Remember, we are using the general formula. This can be ethanoic acid. If I want to be specific, I can use ethanoic acid, propanoic acid. But I don't want to go specific, but whatever I have done, the explanation given to this is the same for all of them. So, but what I'm trying to justify why alkanoic acid have a higher boiling point than alkanols. Now, the explanation first, I want to demonstrate hydrogen bonding in alkanoic acid. I will now demonstrate hydrogen bonding in alkanols. Now, for the alkanoic acid, the hydrogen bonding, to demonstrate it, is what I have done by simply recalling the structure of alkanoic acid. Having recalled the structure of alkanoic acid, I told you that in this is the structure, and in this form it cannot undergo hydrogen bonding, except this double bond must be removed. There has to be a single bond here, which is why there has to be what we call mesomeric shift. The pi bond here is shifted or transferred, and when that happens, it will now be on top of this oxygen. At the end of the day, there is a negatively charged center here, there is a positively charged center here, there is also a negatively charged center on the oxygen. And why is the oxygen negatively charged? I said because this bond here, though this bond here was formed by covalent bonding, and so but because of what this molecule is to go into, this oxygen needs to have become negatively charged, or has to acquire a charge. The hydrogen here has to acquire a charge. The only way they both can acquire charges is by oxygen withdrawing more of the bonded electrons here to itself, and when that happens, the oxygen become negatively charged while the hydrogen become positively charged. And I said, why this is taking place on this molecule, it is also taking place in another molecule. You see, why if I take this to be ethanoic acid and I take this for propanoic acid, why this is taking place here, it's also taking place in propanoic acid, though the two molecules are the same in terms of what their structural formula. And so at this point, there will be now interaction between you see, this negative will be attracted to this positive will be attracted to this one. At the end of the day, you have this hydrogen bond. This is also what? Hydrogen bond. What do you see? It means that when two molecules of alkanoic acid interact, two hydrogen bonds are formed. When two molecules of ethanoic acid interact, two hydrogen bonds are formed. Remember that these are the bonds that must be broken before this molecule will become vaporized. Remember that this molecule is in a liquid state, and so if you want to vaporize this molecule, you will need to what? Break this bond. And if you need to break this bond, you need to you will need more energy, because there are two. If you needed 5 kilojoule to break this bond, then you will need 10 kilojoule, because there is another one here. Now let's see what happens in alkanols. For alkanols, this is the general formula of what? The alkanols. The general formula of alkanols is this. You may decide to represent it this way. Now, for alkanols, what do you see in this case? Now, again, this will become partially what? Positive. This will become partially negative. The same explanation. There will be what? Electron withdrawal at that point. Now, this molecule will now interact with its another molecule, either another alkanol. If this is ethanol, it may want to interact with propanol. If this is propanol, it may want to interact with hexanol. It doesn't really matter the type, the carbon number of carbon atoms involved. What is important is that so long as they are alkanols, they will behave the same way, because they have the same functional group. And so this molecule it will interact with another alkanol. If I take this, supposing I say this is another alkanol, let's say this is another alkanol. Now that's another alkanol. So what you see, there will be interaction. This hydrogen will now be attracted to this negative. Of course, this oxygen is negatively charged, while this hydrogen is positively charged. There will be interaction there, and that interaction is what? Hydrogen bond. Now, comparing the two, you notice when two molecules of the alkanols are interacting, only one hydrogen bond is formed. But when two molecules of when 2 moles of alkanoic acid are interacting, what do you see? 2 hydrogen bonds are formed. When 2 moles of alkanols are interacting, only 1 hydrogen bond is formed. Therefore, it means that more heat, you need more heat to vaporize the alkanoic acid, because there are 2 hydrogen bonds. You need more heat to break the 2 than you will need in the case of alkanol, where we have only 1 single hydrogen bond. So this is why we say that there is high boiling point. The boiling point of alkanoic acid is higher than that of alkanols. You may see in some example, they will explain boiling point in alkanoic acid is higher than that in alkanol. Explain. Sometimes they go specific. They can tell you that the boiling point of hexanoic acid is higher than the boiling point of hexanol. Explain. The same explanation. So I want to believe you have understanding of hydrogen bonding. Like I told you earlier, please check. If you go to the comment section, you will see a link. The link that will help you access my videos or lectures on ionic bonding and covalent bonding. And please watch this video so that you have absolute understanding of bonding. Remember again that this channel will do we treat all topics for chemistry, mathematics, and physics, and we also offer lectures on medical topics, on medical conditions. So please, I will request you hit the subscription button, also turn on your notification bell so that when new videos are made, you'll be first to be notified. Again, share and like the video. Thank you.